Let's start with something that sounds simple. Planets spin. That's it. That's the rule. When a star forms, it begins as a spinning cloud of gas and dust. Gravity pulls everything inward, and as the cloud shrinks, it spins faster, like an ice skater pulling in her arms. Out of that spinning disk, planets form. And because they form from that disk, they inherit its direction of rotation. Same direction, same sense of spin. Orderly, predictable. Most of the planets obey. And then there's Venus. Venus doesn't just spin slowly. It spins backwards. Now, backwards doesn't mean upside down in space. Space doesn't have an up or down. It means that if you could stand on Venus and watch the sky, the sun would rise in the west and set in the east. The planet rotates clockwise, while Earth rotates counterclockwise. And that's already strange enough. But it gets worse. Venus rotates so slowly that one full spin takes 243 Earth days, yet it goes around the sun in only 225 Earth days. So its day is longer than its year. Think about that. The planet turns so lazily that it finishes an entire orbit before it finishes a single rotation. If you were expecting the universe to behave neatly, Venus is your first disappointment. Now here's the part that bothers physicists. When something breaks a pattern, you ask, what force did that? Because angular momentum, the thing that makes objects spin, is stubborn. It doesn't just flip casually. It resists change. To reverse a planet's spin, you need something big, very big. So what happened? Did something hit it? Maybe. But you don't flip a planet gently. You'd need a titanic collision. And if that happened, you'd expect dramatic consequences. Changes in orbit, debris, scars. Venus doesn't make the story that simple. And there's something even more subtle hiding here. If the early solar system was just a swirling disk governed by clean physical laws, then Venus should not be unique in this way. Why is it the only major planet that fully committed to this reversal? Uranus is tilted dramatically, yes, but tilted isn't reversed. Venus made a different choice. Nature usually prefers economy. It doesn't create exceptions unless there's a mechanism demanding it. So either there was an extraordinary event, or our simple spinning disk story is missing something. And that's where the discomfort begins, because we love elegant origin stories. A rotating nebula forms planets. They spin consistently. The math works. The models are clean. And then one planet right next door says no, not violently, not dramatically, just quietly, stubbornly, spinning the wrong way. And the most unsettling thing isn't that Venus rotates backwards. It's that we can describe the anomaly in exquisite detail, measure its period, calculate its angular momentum, simulate scenarios on supercomputers, and still not point to a single inevitable explanation and say, that's it. That's why Venus sits there, glowing brightly in our sky, as if nothing is wrong. But its slow backward spin is a whisper, a reminder that the universe is not obligated to follow the stories we prefer. And sometimes the most interesting physics begins exactly where the pattern breaks. So suppose we try the most dramatic explanation first. If a planet is spinning the wrong way, maybe something hit it. That sounds satisfying, doesn't it? Early solar system, chaotic, violent, objects flying everywhere. A young Venus gets smashed by a protoplanet the size of Mars. The impact is off-center. Angular momentum flips. End of story. Except physics doesn't like stories that end that neatly. When you reverse the spin of something as massive as a planet, you are not nudging it. You are performing an act of cosmic brutality. Angular momentum is not a polite quantity. It resists change. To stop Venus's original rotation and then push it the other way requires an enormous transfer of energy. Now here's the first complication. If the collision were large enough to reverse the spin, it should have left fingerprints, not just a flipped rotation, but alterations to the orbit, possibly a significant tilt, maybe debris forming moons. Earth, for example, likely suffered a giant impact that formed our moon. That event left clear consequences. Our unusually large satellite, our axial tilt, geological clues. Venus, no moon, nearly circular orbit. Modest axial tilt. If it was hit hard enough to flip its spin, it somehow avoided leaving obvious evidence. That's inconvenient. So perhaps it wasn't one collision. Maybe it was many smaller ones. Over time, repeated impacts gradually slowed the planet's original spin, bringing it to a halt. Then additional nudges tipped it into retrograde motion. But now we have another issue. Impacts are random. They don't politely coordinate. If multiple collisions are responsible, why did they conspire to produce such a slow rotation? Venus doesn't just rotate backwards. It rotates extraordinarily slowly. A single day takes 243 Earth days. That's not just flipped, that's drained. If impacts were common enough to do this, why didn't Earth end up similarly sluggish? Why didn't Mars die? This explains the possibility, but not the uniqueness style. Computer simulations tried to reproduce this scenario. Computer simulations try to reproduce this scenario. They can flip a planet's spin under certain impact angles and speeds, but the parameter space is narrow. You need just the right size object, hitting at just the right angle, at just the right time in Venus's formation history. It's possible, but possible is not the same as inevitable. And there's something else that nags at you. A collision violent enough to reverse a planet's rotation would dump tremendous heat into the system. Venus today is infernally hot, yes, but much of that heat is atmospheric greenhouse effect. The rotational flip would have happened billions of years ago. The thermal story must still add up. When you stack all of this together, you don't get a clean answer. You get a scenario that works if the dice landed just so. Now, nature does roll dice. The early solar system was not a clockwork machine. It was messy. Things crashed, orbits shifted, chaos ruled. But when we leaned too heavily on a big accident did it, we risk mistaking plausibility for explanation. It's tempting to say Venus is simply the unlucky victim of a cosmic car crash. Yet the more you calculate, the more you realize how delicate the reversal must have been. Not just to flip the spin, but to leave the planet otherwise so ordinary. And that's when you begin to suspect that the collision story might be less of a solution and more of a placeholder. A way of saying something big happened without truly knowing what. All right, so suppose we abandon the idea of a single dramatic collision. Suppose Venus wasn't flipped like a coin struck by a hammer. Suppose instead it was persuaded, slowly, because Venus has something unusual about it, not just the backward spin. The atmosphere, if you could stand on the surface, which you cannot, because you would be crushed and cooked, you'd discover that the air above you weighs about 90 times more than Earth's atmosphere at sea level. It's mostly carbon dioxide, thick and massive, wrapped around the planet like a heavy blanket. Now here's where things get interesting. The sun heats that dense atmosphere unevenly. As Venus rotates, even very slowly, the sun pulls gravitationally on the atmospheric bulges created by heating. Those bulges don't line up perfectly with the sun because the atmosphere has dynamics of its own. Winds move, heat shifts. The bulge gets dragged slightly ahead or behind. And whenever you have a gravitational pull acting on something offset from alignment, you get torque. Torque changes rotation. This is not exotic physics. It's the same reason our moon is tidally locked to Earth. Gravitational forces create torques that gradually adjust spin rates. Over long periods of time, they can do remarkable things. So the idea goes like this. Early Venus may have been spinning in the normal direction, but solar tidal forces acting on its thick atmosphere slowed it down, slowed it further, perhaps brought it nearly to a halt. And then, because of the details of how the atmosphere and the solid planet interact, the torque could push it the other way. No catastrophic impact, no violent flip, just billions of years of subtle gravitational persuasion. Elegant, isn't it? Hyph, but elegance is not proof. The tidal torque explanation depends sensitively on details. The thickness of the atmosphere, the rate at which heat is transported, the internal friction between the atmosphere and the planet's surface. Even the initial rotation rate matters enormously. Change those parameters slightly, and the outcome changes dramatically. In some models, Venus ends up tidally locked, always showing the same face to the sun. In others, it slows but never reverses. In a narrow range, it becomes the retrograde world we see today. That narrowness is unsettling, because when a theory works only under finely tuned conditions, you begin to wonder whether you are uncovering inevitability or arranging the numbers until the answer fits. And there's another subtle point. Venus's current rotation period, 243 Earth days, is suspiciously close to a resonance with its orbital period. The numbers almost talk to each other. That suggests a long gravitational negotiation between the sun and the planet. But negotiations imply stability. How did the system avoid settling into a simpler end state, like tidal locking? Why did it land precisely in this slow backward rotation instead? The tidal model tells a plausible story. It uses real physics, real equations, no miracles required, and yet the explanation feels delicate. It suggests that the backward spin of Venus may not have been a dramatic event at all, but the cumulative result of tiny forces acting persistently over immense time, which is in some ways more astonishing than a collision, because it means that something as intangible as hot, moving air, given enough time, can reverse the spin of an entire planet. That's the power of torque. But it also leaves us with a discomforting truth. The answer may lie not in a single spectacular cause, but in the quiet amplification of small effects. And small effects are notoriously difficult to reconstruct billions of years later. Let's imagine the early solar system not as the tidy diagram you saw in a textbook, with clean elliptical orbits and evenly spaced planets, but as something far less civilized. It was a gravitational bar fight. Massive bodies were still forming. Protoplanets were migrating. Angular momentum was being exchanged like loose change. Like loose change, nothing had settled into the calm configuration we see today. The system was dynamically alive and unstable. In that kind of environment, rotation is not sacred. Take Venus. Early on, it may have been spinning rapidly in the same direction as the rest, but gravitational interactions with nearby forming planets, particularly Earth, Jupiter, and the debris disk, could have introduced small, repeated perturbations. Each tug slightly altered its spin axis. Each resonance nudged its rotational state. Now here's the important part. Nonlinear systems don't behave politely. When a system is nonlinear, small changes don't always produce small effects. Sometimes they amplify. Sometimes they cascade. Sometimes they push the system into an entirely different configuration, one that would have seemed improbable at the start. Planetary rotation, especially when coupled to orbital resonances and tidal effects, is one of those systems of early solar system dynamics. Shows something fascinating. Some computer simulations of early solar system dynamics show something fascinating. Under certain conditions, a planet's axial tilt and spin direction can wander chaotically, not smoothly, not predictably, but erratically. The spin axis can wobble. The rotation rate can fluctuate. And occasionally, not often, but occasionally the rotation can flip. Not because something struck it, not because a single force demanded it, but because the system wanted there. Chaos in physics doesn't mean randomness. It means extreme sensitivity to initial conditions. Two nearly identical starting points can diverge wildly over time. If you could rewind the solar system and run it again with a microscopic difference, a slightly shifted orbit here, a slightly different mass distribution there, Venus might end up spinning normally, or it might spin backwards, or it might be tidally locked. The point is not that chaos explains everything. It's that chaos allows for outcomes that don't require special pleading. In a chaotic dynamical environment, retrograde rotation may not need a dramatic cause. It may simply be one of many possible stable endpoints. But here's the part that keeps physicists uneasy. Saying it was chaotic is not the same as understanding why the present configuration persisted. Chaos can move you into an unusual state, but stability keeps you there. Why did Venus settle into this particular slow retrograde? E-rotation instead of drifting into tidal locking with the sun? Why didn't subsequent gravitational interactions knock it into a different state? If the early solar system was truly chaotic, then Venus is a fossil, a frozen outcome of that instability, a survivor of a dynamical lottery, and lotteries raise uncomfortable questions. Because if outcomes depend sensitively on initial conditions we can never fully reconstruct, then our explanations become statistical rather than deterministic. We stop saying, this happened because of that, and start saying, given enough chaos, something like this was bound to happen somewhere. Venus may simply be that somewhere, but there's something humbling in that idea. It suggests that planetary histories are not clean mechanical stories, but contingent narratives shaped by fragile early conditions. And if that's true, then the backward spin of Venus isn't a glitch. It's a reminder that the solar system we see today is not the only one that could have been just the one that survived. There's a temptation in science that's very hard to resist. You build a model, you write down the equations, you plug in the numbers. The output resembles what you observe. And then, almost without noticing, you begin to feel that you understand. Not that you can calculate, but that you understand. Richard Feynman used to warn about this. He pointed out that being able to manipulate symbols or repeat an explanation does not mean you have grasped the underlying reality. Nature is not obligated to match the stories we tell about it. Now think about Venus. We have explanations for its backward rotation. We have impact simulations. We have tidal torque models. We have chaotic dynamical analyses. Each of them produces retrograde rotation under certain conditions. Each of them can be made to fit the data. So the danger is better, because when multiple models can reproduce the same outcome, we feel reassured. Look, we say physics can explain this. But what have we actually done? We've shown that the equations allow such a configuration. That's not the same as knowing which mechanism actually occurred. Feynman would push further. He would ask, if you had to bet your life on which explanation is correct, the giant collision, the atmospheric torque, the chaotic evolution, could you? Or are you comforted merely because at least one of them seems plausible? Vite it. There's a difference between plausibility and inevitability. If an explanation requires carefully chosen parameters, stipple just the right impact angle, just the right atmospheric density, just the right resonance timing, then you must ask whether you're discovering nature or tuning a narrative. And here's the uncomfortable part. The mathematics doesn't protest. The equations are happy to generate many possibilities. They don't tell you which one history selected. Physics is extraordinarily powerful, at predicting what can happen. It is less powerful at reconstructing what did happen when the evidence is billions of years old and largely erased. Venus doesn't come with a label that says flipped by impact at 3.9 billion years ago. It simply rotates slowly and backwards, offering us only its present state. So when we say we understand Venus, what we really mean is something narrower. We understand mechanisms that could produce Venus and matters. That distinction matters because confidence without precision is a kind of illusion. And Feynman distrusted illusions more than ignorance. Ignorance is honest. Illusion pretends. The backward spin of Venus exposes this beautifully. It forces us to confront the limits of reconstruction. It reminds us that fitting data is not the same as uncovering history. And perhaps that's the deeper lesage. Son, the universe is under no obligation to provide us with uniquely solvable puzzles. Sometimes it gives us multiple consistent stories and withholds the decisive clue. When that happens, the honest position is not triumph. It's humility. Venus keeps spinning the wrong way. Venus keeps spinning the wrong way. Our equations keep offering explanations. And somewhere in that gap between mathematical possibility and historical certainty lies the warning. The warning that understanding is not something we declare. It's something we earn carefully, reluctantly, and only when the alternatives have truly been ruled out. Until then, we should say what science says at its best. This is what might have happened, and mean it. There's a quiet arrogance that can creep into our thinking about the universe. We look at the sky, measure the motions, write down the laws, and gradually we begin to feel that the big picture is settled. Planets form from disks, orbits stabilize, systems mature. It all seems orderly, almost inevitable. And then there's Venus turning the wrong way, not dramatically wrong, not explosively wrong, just persistently, stubbornly wrong. And that should bother us more than it does. Because if you step back, Venus is not some distant exoplanet orbiting a star 1,000 light years away. It's next door. Astronomically speaking, it's in the same neighborhood. We can bounce radar off its surface. We can measure its rotation period down to astonishing precision. We know its atmosphere, its temperature, its pressure, and yet we cannot say with certainty why it spins backwards. That's not a failure of intelligence. It's a boundary marker. It tells us something about the limits of reconstruction. We are very good at predicting forward. Give us initial conditions and laws, and we can calculate trajectories beautifully. But give us the end state billions of years later and ask, what exactly happened? That's a different problem entirely. Venus forces us to admit that planetary history may be less deterministic than we'd like. Consider what this means beyond our solar system. When we observe distant exoplanets with strange tilts, eccentric orbits, or retrograde motion relative to their stars, we often construct narratives: migration, resonance, impacts, tidal evolution, and those explanations are grounded in real physics. But Venus reminds us that multiple pathways can lead to similar outcomes. The present configuration does not uniquely encode its past. That should inject caution into our certainty. And then there's Earth. It's easy to assume Earth's status, stability, its moderate rotation, its axial tilt, its relatively calm orbital history is simply the natural outcome of planetary formation. But what if it's just one of many possible survivors? What if small differences early on could have left Earth spinning wildly, or locked to the sun, or reversed like Venus tack? The line between normal and anomalous may be thinner than we think. Venus is not just an oddball planet. It's a counterexample to complacency. It whispers that planetary systems are shaped by contingencies, by interactions that amplify tiny differences into lasting consequences, into lasting consequences. And here's the deeper discomfort. If something as fundamental as a planet's rotation direction can hinge on delicate early conditions, then the architecture of a solar system is not merely the unfolding of clean laws. It is the unfolding of laws through unstable environments. Physics provides the rules. History selects the outcome. Venus stands as evidence that the rules allow more variety than our intuition prefers. So the warning is not that science has failed. The warning is subtler. Do not mistake coherence for completeness. Do not assume that because the equations are elegant, the history must have been simple. Venus turns slowly backwards under a thick, crushing sky. And in that slow inversion is a reminder that the universe is not obligated to match our expectations of order. Sometimes the exception is not a glitch. It's a clue that the story is larger than the version we've told ourselves. Dot way.